To get back to what we were discussing last time, we were talking about the probabilistic method, which if I mean, we kind of embodied a basic version of probabilistic method in this simple statement that if you have some random variable that the expectation of z is greater than or equal to c, then there is some outcome on which z of omega is greater than or equal to c. And in fact, you can look at the proof we did, and you will also observe that there is some outcome which occurs with positive probability. Because if the outcome doesn't occur with positive probability, you might as well have deleted it from your outcome space if it never actually occurs. And in the entire computation we did in the proof of this, you can see that this is an outcome with positive probability. So another way of thinking about the probabilistic method, which we'll come back to again, is what you are proving is that the probability of whatever you want to happen is positive. So there is an outcome which makes z greater than or equal to c happen, and this is some sort of maybe good event that you are interested in happening, sort of a good object that you are interested in the existence of. And your outcome space contains this kind of object with positive probability. So it at least sort of shows up sometimes. And because it shows up, it at least exists. And so it's a useful way of showing existence of interesting objects, which we might not even know exist otherwise. And it's a surprisingly powerful way. There have been many objects, like really good codes, or maybe really nice kind of graphs, for which it took decades between when we could just show that they exist and when we could actually find or construct them, sort of give some sort of a constructive proof. And I mean, in some cases, we still don't know of really good objects which we can show exist, but we have no idea how to actually construct them. But in some sense, so the probabilistic method is a powerful way of showing existence, sometimes even a little too powerful, because lets us prove existence of all kinds of good stuff, and we have no idea how to actually find them. And just the way we applied it, just an observation about it, is that can prove it by existence, by computing existence of z, or the expectation of z. And in general, I mean, this is not necessarily a comment about the probabilistic method. It's easier, in many cases, it's easier to compute expectation of z by writing it as a sum of simpler random variables. In a lot of settings, we saw random variables which were either 0 or 1, and then use linearity of expectation. So we'll see another example of the same phenomenon right now, and you'll also see an example in the next homework. So this is something which, and then this sort of trick of writing it as a sum of simpler random variables is something we'll pretty much be doing all the time when we work with any kinds of interesting random variables. So we will see it in a lot of settings. Any questions about what we discussed last time? Okay, so let me talk about one more example of the probabilistic method, or this sort of technique of showing existence of objects. And this is in the setting of what is called independent set, or rather, again, the optimization problem of finding the maximum independent set. Sorry. like we talked about 3-SAT, the maximization version of 3-SAT, where the goal was to satisfy as many clauses as possible. Maximum independent set, the goal is to find the largest independent set. And what is an independent set? It's given a graph, it's a subset of vertices such that this set contains no edges. So there are no edges for which both endpoints are in our set S. Okay. So why is this called independent? Well, sometimes we think of edges as some sort of dependencies or relation between these nodes. And when you find an independent set, you're kind of trying to say that the nodes that you have in your set S have no relation or no dependencies on each other, and you can sort of view them as sort of degrees of freedom or sort of independent choices, and you don't have to think about other nodes when you choose something for a node in S. And just as an example, we're given a graph. We can try to see if we can find an independent set. I'm not sure if this is the maximum independent set, but we can try to find something. So let's say we select this vertex. Then because we want no edges to be contained, we can't select these vertices. These are not allowed. But maybe we can select this vertex. And now just because we selected this vertex, these vertices are not allowed. But maybe we can select this vertex. And now we have a bunch of disallowed stuff, but maybe we can select this one. And at this point, I don't think I can select any more vertices. I think maybe I can select this one. Okay, so I did find an independent set of size 5 in this graph with, let's see, I have 11 vertices. So that's, I'm not sure if this is the maximum for this graph or not, but in general, it's an NP-hard problem to find the largest size independent set. And in fact, the problem is really notoriously hard to even approximate. So there are known results in terms of how hard this problem is to approximate. And basically, in a graph with n vertices, we can't even approximate the size of an independent set up to n to the 0.9999. So you can not even give any kind of non-trivial approximations. But in this case, we will say that you can show existence of some sort of independent sets. But let's first start with a simpler case where we don't need the probabilistic method. So suppose I tell you that your graph is such that the degree of every vertex is bounded. It's at most t. And the degree of any vertex is just the number of edges incident on it. So the number of neighbors it has in the graph. Then I claim that you can always find an independent set of size n over d plus 1. This may not be the maximum independent set. For example, if you try to compute this bound for the graph we gave, n is 11, the degree of vertices, there is at least one vertex of degree 4. So the best you can say is maybe that the degree of every vertex is less than equal to 4, but 11 over 4 is not the best bound on the size of the independent set. It's not the, and in fact, we did find an independent set of size 5. So this may not be the best construction, but it can show that there is at least one large independent set. And pretty large if d is small. If d is, let's say, a constant independent of the size of the graph, then it's a pretty large independent set. Any guesses for how to prove this? I'm claiming that you don't really need any probability or anything for this. It's
Really quickly, is this for constant D? So each vertex has exactly D edges?
No, it's at most D edges. So
Okay.
it need not be the same for every vertex. But even then, this is bound is true. Of course, when it is exactly D, it's still less than equal to D, so it still applies, but the condition is a bit more general.
Okay.
And I'm not assuming D is constant, but the bound is more interesting when D is constant. So D can be, let's say, n over 2, and then the bound is n divided by n over 2 plus 1, which is not so interesting. It's roughly about half, slightly bigger than half, which is not that great as a bound. So, I mean, of course, these are extremes. It's the bound is very interesting even when D is something like, say, log n or root n. So it still gives us some very interesting bounds. The problem is, yeah, we need the same bound on the degree of every vertex. We have to say that every vertex degree is bounded by square root D. So this doesn't quite allow for the situation where there's some vertices with very high degree, but most of the others have very small degree, and it doesn't really give us. I mean, maybe we can kind of do some hacky analysis, but the bound as stated does not really give us interesting results there, because if there is even one vertex of degree n over 2 and everybody else has degree 2, in some sense, the bound will be just depending on the worst degree. Does that answer your question?
Yeah, absolutely. Thank you.
Okay, but at least if you want to just prove this bound, I claim we can prove it relatively simply. Yes, this is a sanity check. And this is actually the process I was just doing. It's sort of just try to look at a vertex and then try to find something else and so on. So just sort of this eyeballing the graph process that I was doing. It's basically a greedy algorithm. I was trying to, I picked one vertex and said, okay, this is an independent set because one vertex never contains an edge. For an edge, you need at least two vertices. Then I kind of look at its neighbors like, okay, these guys have an edge incident from one of the vertices I picked, so I can't really pick them. Let me try to pick one of the others. Okay. So uh, we kind of had this algorithm that pick a vertex I, and then so we had this algorithm that pick a vertex, rule it out, rule out its neighbors, and then repeat. But the nice thing is, because the degree is bounded by D, I rule out at most D vertices at any given iteration of this procedure. So basically, every time I pick one vertex, I rule out at most D. So sort of out of these at most D plus one things that I considered at this step, I got to pick at least one. So overall, I will pick at least n over D plus one, because at every iteration of this procedure, the total number of vertices which I have not looked at so far sort of goes down by, so I can maintain two counts. I can maintain the count of size of S. This goes up by one at every step, at each step. And I can maintain a count of vertices which I have not looked at so far. And this goes down by at most D plus one at any step. I look at the vertex that I do pick to include in set S, and I look at all its neighbors, which I sort of rule out as possibilities. So basically, for every D, sort of at most D plus one that I rule out, I get to include it at least once. So I will include at least n over D plus one vertices. Is that okay? Okay, so that's just a simple greedy bound. I didn't really need to do anything very sophisticated to prove this. A more interesting bound, which can say that Well, we can pretend that as if every vertex had this contribution of 1 over degree plus 1. So if you replace the degree of I by the largest degree, uh, mm, let's say D max is the largest degree in the graph, which is what we were calling D on the previous slide. Then this would recover the bound on the previous slide. But it can potentially be better. So if there are some vertices with a very small degree and some vertices with large degree, this bound still gives us a very interesting value. It is, the vertices with small degrees don't have to pay for the ones with very large degrees. Okay. And this we will show using the probabilistic method that a large independent set of this particular size exists. But yeah, I'm not going to show a procedure for finding it. Although we can, yeah, I mean, at least show a random procedure basically. Okay. Any questions about the bound before we prove it? So actually, we can show the existence and basically give at least a random procedure for finding this kind of an object. So it's the proof is just saying that let's do what we did, except let's sort of look at vertices in a random order. Okay. So what do I mean by that? So let's arrange the vertices in some order, okay. Not necessarily in the order 1 to n, but some random order. So, okay. And now let's do what we were doing before. Let's look at some vertex, look at its neighbors and rule them out. So its neighbors might not be next to it in the order. They might be somewhere in this. Okay. And then we rule out the neighbors. Because if we pick this vertex, then we cannot pick its neighbors. And then we go to the next vertex, which we haven't ruled out. So let's make it a little more interesting. Let's say we did rule out this next one. Then we go to the first vertex that we haven't ruled out so far. And let's say we include that one. And then rule out its neighbors and so on. So this is doing exactly what we did in the previous algorithm, or just kind of this random or greedy in this greedy procedure. But now it's doing it in a sort of in a random order. It's just processing the vertices in a random order. And this it's a random procedure, but it can it's giving you a way of finding a large independent set. And I claim that it's actually finding an independent set of the size we wanted. So let's say Z is equal to the size of the independent set we find this way. I will claim that the expectation of Z is at least whatever we have here. So in particular, there exists an independent set of this size. Okay, is the strategy clear? I still need to prove to you that the expectation of Z is whatever I claimed. And by the way, yeah, I guess we've been assuming throughout that the graph has n vertices. Okay. As before, it's turns out to be easier to analyze the expectation of z by thinking of it in terms of a sum of simpler random variables, which is, let's say, x1 to xn. And let's say xi is, again, 1 if I is in this independent set and 0 otherwise. So if we picked I, xi is 1. Okay. So xi can be sort of, whether we pick I or not, it really depends on where it might be in the ordering. For example, if the ith vertex was in the first place in the ordering, then we are always going to pick it. But if it's later in the ordering, but it's still before all its neighbors, then it's still going to be picked, because it's never going to be ruled out. And if it's not ruled out, it's only ruled out if some of its neighbors come before it. And then we kind of cross it out because we looked at the neighbor first. So a vertex is picked if and only if so in the order in which we are looking at things, as long as I comes before all its neighbors, we pick the vertex I to be in our independent set. Is that okay?
Sorry, I'm a little bit confused. What are the can you re-explain the x1 to xn again really quick?
Yeah, absolutely. So x1 to xn are random variables which take values 0 or 1. And xi is 1 if we pick the vertex I to be in our independent set. If we pick it to be in our set. And when do we pick things to be in our set? Well, so let's in this kind of, I've indicated picking things by this check mark or this green underscore. So we looked at this vertex, we picked it to be, or we included it in an independent set. Because we included this vertex, we cannot include any of its neighbors, so we sort of ruled them out. Okay. Then we looked at the next vertex, which we hadn't already ruled out. So this one we had ruled out, so we did not look at it. Then we looked at this one and then picked it to be in our independent set because it was not yet ruled out. And then we will need to look at all its neighbors, maybe here, and rule them out. And then we will look at the first vertex, which we haven't ruled out yet. So, and so on. So xi is 1 if I got picked before it was ruled out, right? If something is ruled out, we don't pick it. And if it's not ruled out, we do get to pick it. That's only two things happen, right? We kind of go through this line, either something before I rules it out, and then we don't pick I, or we reach I and it's not been ruled out yet, in which case we'll pick it. Is that okay?
Yeah, that's good. So that in this case, never mind. Yeah, I just answered it.
Okay. Right. So the thing is, yeah, we need to figure out precisely what is the probability for picking I, or at least somewhat precisely. And I claim that, I mean, we kind of define this sort of complicated process of we kind of rule some things out, then pick the first one that is not ruled out and keep repeating this. But from the perspective of the vertex I, the analysis is very simple. Let's say this vertex I has 5 neighbors. So it has degree 5 in the graph. Then no matter what happens to all the other vertices, what happens to I only depends on what happens to its neighbors. Right? Because the only vertices that can rule I out are its 5 neighbors. Nobody else can rule out this vertex, because when you rule something out, you only rule it out because you considered a neighbor of it, and then the neighbor kind of had an edge, and you kind of cross out everything that is at the end point of that edge. So, so let's, if we have if the degree of this vertex is 5, then all we need to look at is the ordering of these 6 vertices. There might be all the other vertices in the graph present on this line, but we don't care about them. So this is just the vertices that I've drawn in bold here are just I and its neighbors. And if one of its neighbors appears before I in the ordering, then we will pick that neighbor and rule I out. Otherwise, we'll pick I and rule out its neighbors. So from the perspective of I, the only way we are going to pick I is if it comes before all its neighbors. Is that okay? Okay, actually, well, it's at least greater than equal to. I mean, so it can happen that maybe we had this ordering, let's say this was I, its neighbor appeared before it's in the ordering, but it was ruled out because of this vertex, and so then we did pick I. But if I appeared before all its neighbors, then nobody has had a chance to rule it out, and then we are going to pick I for sure. So at least true that the probability that we pick I is at least the probability that I is considered first before we had a chance to look at any of its neighbors. Is that okay?
Yeah, I think that's good.
Okay. So, and the probability that we pick I before all its neighbors is easy to calculate, because now we are just looking at the order of these 6 vertices. We don't really care about what happens in terms of the ordering to the entire graph. We just care about what happens to these 6 vertices. And something which needs checking, but so if we have a random order on all the vertices on the graph, so if we have one of the n factorial permutations, when you look at the order of these 6 vertices, there are 6 factorial or 720 possibilities, and each one of them is equally likely. So you can kind of go backwards. You can say, what is the probability that I kind of fix a particular order of these 6 vertices, and then the ordering on the total n vertices is such that for these 6 vertices, I get this particular ordering that I have picked ahead of time. And you can check that the probability is equal no matter what ordering you pick on these 6 vertices ahead of time. So that's a little bit of just combinatorial counting, and you can check that. So in this particular case, when degree of I is 5, the probability that I is picked before all its neighbors is the probability that you pick one of the 6 factorial permutations and I is in the first position. Do you know how much that probability is?
One over di plus 1.
Right. So this particular case, if we are looking at 6, what is this then? How many permutations are there in which I is appearing in the first position out of these 6? Well, let's put I in this first position, and then you have 5 factorial ways to get the rest of them. So it's 5 factorial divided by 6 factorial, or 1/6 in general. The probability that I is picked before all its neighbors is greater than equal to 1 over the degree of I plus 1. And then we are done, because then expectation of C is greater than equal to summation over I, 1 over degree of I plus 1.
One question, why
Yeah.
is Pxi equals 1 greater than equal to the probability I comes before? Not equal.
Because, sorry?
Why is it not equal?
Yeah, I was maybe confusing myself, but let's see. I was thinking of this particular case where, let's say this is I, okay, and we pick this vertex. Or sorry, maybe I was indicating that by green. Right. So let's say we picked this vertex, and so we will rule out all its neighbors. So we are never going to pick this particular one. And even though this was a neighbor of I, and it did come before I, so it did not happen that I comes before all its neighbors, but xi was still 1 in this case. Isn't that correct?
Makes sense, yeah.
Yeah. So yeah, I think I initially said that's equal to, but no, it's at least greater than equal to. That if I comes before all its neighbors, then nobody has had a chance to rule I out yet, so it's going to be picked for sure. And at least that's something we can calculate easily. So and then that gives us a fairly interesting bound anyway. Okay. Okay. Yeah, I mean, the advantage of sort of just considering this lower bound is that then we kind of eliminate all kind of complicated interactions we have because of other vertices and sort of maybe chains, so that they can rule out neighbors of I before they have a chance to rule out I first, and so on. Overall, in general, this sort of can be a complicated chain of events, but particular lower bound is a very simple lower bound. It only depends on I and its neighbors and not on anything else.
Really quickly, this could be a simple question about the expectation.
Absolutely.
So I understand that the probability that xi equals 1. So in the right side on the sum, we're multiplying by an implicit 1 because xi is equal to 1.
Yeah, I mean, we are kind of just using this fact that expectation of xi is equal to the probability of xi is equal to 1. This is something which we, I think, said when we were talking about variables which take values 0 or 1. Anyway, I mean, yeah, so you are multiplying by an implicit 1 because you say that the expectation of xi, you can do it either at this point or you can do it later in the summation, but I prefer to do it at this point just because it's a fact we can remember about all variables which take values 0 or 1, is that the expectation is nothing but the probability that the variable is equal to 1. Right. So, and in general, I think I also tried to emphasize this earlier, and let me say it again. It's a very useful fact to remember that when you have a variable which takes values 0 or 1, its expectation is equal to the probability it's 1. And so expectations obey this kind of linearity of expectations. Probabilities don't, but in this case, because expectation can be written as some probability, you can apply linearity of expectation, sort of say that I'm going to compute xi, sort of expectation of xi, then come down to understanding probabilities, because expectation of xi is just equal to some probability. Does that answer your question?
Okay, awesome. Yeah, thank you. Thank you.
All right, good. So yeah, I mean, we will use this fact again and again. If you decompose into a sum of random variables which are 0 or 1, then expectation of xi is just some probability, and it can sometimes be easier to understand this probability. All right. So now, as I said, what we were doing so far can be put as the sort of showing that maybe the probability of some good event is greater than 0, and this good event is whatever we might be interested in. In this particular case, maybe that z of omega is greater than or equal to c, where c is kind of measuring some notion of goodness, or it's measuring some property or some parameter we are interested in. And it's the probabilistic method kind of show whatever we want to happen. There is a large independent set, or there is assignment to 3 sets satisfying many many clauses, or there is a good code with kind of some large error correction properties. The probability of such an event is greater than 0, so such an event at least happens. Stronger statements, which are often sort of obtained via tail bounds, but these statements will be of the form that the probability of some bad event is less than epsilon. So instead of saying some positive bound on the probability of a good event, we will say, and at least assuming some sort of dichotomy between good and bad, or just sort of defining bad to be everything that is not good. No moral judgments here, by the way. It's we get to say that the probability of our good event is at least 1 minus epsilon. So in some sense, the tail bound lets us conclude stronger statements. It says that I mean, and depending on the application and depending on the kind of bound we are using, and we will see, this epsilon can be something which is kind of going to 0 in the limit, or it can be something fixed but small, like 1/10 or 1/3 even. But as long as it kind of gives us the right kind of bound on the probability of whatever events, good events we are interested in, and we'll see applications and we'll see what these bounds look like. I'm calling them tail bounds because they're usually obtained by. So let me kind of get to it and show you the kind of bound I'm looking at. So they're usually obtained by saying that some random variable is the probability that some random variable is large or is kind of very far from some point is small, and that we kind of view as the tail of the random variable when it's sort of far from the central area of its distribution. And then we'll see again more illustrations of this. And it's up to us to set up a random variable which is such that the tail of the random variable corresponds to the bad events that we want to rule out. And in some sense, the central area corresponds to the good events that we have in mind. It's not that there is any sort of inherent notion of sort of being good in the fact that the random variable is not too large or anything. That's something we just set up, and we model the problem in such a way, and we'll see examples how to model the problem in such a way. But before going to the modeling aspect of it, let's just talk of a couple of inequalities real quick, which we will use to prove the bounds we want. The first, which is called Markov's inequality, it's really a very simple inequality, but at the same time, one of the most useful ones, because as you will see, all the other inequalities are just a fancier version of Markov's inequality. So we will basically be applying Markov's inequality all the time. Okay. Any questions about the statement before we start?
Can you
notice?
Go back one slide?
Yeah. Okay. Yeah, I should have done that. Notice that we are saying that z is a non-negative random variable, and what I mean by that is, so z is a function, right? And what does it mean to say that a function is non-negative? It just means that on every single input, the value of the function is non-negative. So a random variable is some function. And when I'm saying non-negative, it means that for every single input, the function is greater than or equal to 0. And then I obtain some bound on the probability that so I know that z is greater than or equal to 0, and I obtain some bound on the probability, let's say that z is greater than or equal to 20, which is expectation of z divided by 20, or expectation of z divided by t in general. This bound is meaningless if the expectation of z is larger than 20 in this case, because it just says the probability is less than or equal to 1, which I knew to begin with. I didn't really need to prove Markov's inequality for that. But it can be interesting in case t is much larger than expectation of z. So what it tells us is that the probability that a non-negative random variable is much larger than its expectation is small. Okay. A non-negative random variable typically is not much larger than its expectation. Okay. And so in some sense, and we'll see, you can kind of another tail bound later in the lecture. We'll see another one in the next lecture, which basically give us stronger and stronger bounds if you know more and more about the random variables. So to apply this particular inequality, all you need to know is the expectation of a random variable. And sometimes z can be so complicated that all we can do is compute its expectation. Maybe it's not even easy to calculate the variance of this random variable. Okay, and we will see that, okay, maybe if we can calculate the variance, we can potentially get a stronger bound, and we'll see that in a minute. And in the next lecture, we'll say that even if we know something even more about z, that it's a sum of independent random variables or some weakening of thereof, then we can get even stronger bounds. So it depends on how much we know, but this is kind of the most vanilla inequality, that at least if you know just two things, it's non-negative and you can calculate its expectation, then already you can say some interesting statements about how large it can be. Does that is the statement okay at this point? Okay, let's assume that's a yes.
Can you quickly go back one slide? I just need to see if the signs I copied were correct.
Yeah. Oh, sorry. Back one slide on that. Yeah.
Yeah. Okay.
So I'm going to put an upper bound on the probability of some bad event, and here I'm kind of thinking of the probability of this bad event as z is greater than or equal to t. As I said, it's up to us to create a z so that sort of bad events correspond to z being large, and we'll see how to sort of construct these kind of random variables. But suppose we did, then we can use this bound. Okay. The proof is not too complicated, but it's a slight rearrangement of the expectation of a random variable. So let's start with so let's say, I mean, the proof applies for random variables defined over infinite outcome spaces, etc. But since we've been dealing with finite or countable ones, let's stick with that, and let's give a proof for that. So let's calculate the expectation of C. And so let's say V ranges over all values So let's say V ranges over all values that Z can take. Again, Z is a random variable defined over a finite or a countable outcome space. So it can only take finitely many values. So I've written a summation, but otherwise we should write integrals and so on. And we'll get to that in a couple of lectures, how to properly deal with random variables over sort of infinite spaces or uncountably infinite spaces. Okay. And now let's say whatever values it can take, we arrange them in ascending order. So let's break this summation into two parts. Over all values which are greater than equal to t and all values which are less than t. And for this part, I'll just say that it's greater than equal to 0. And this is where I'm using non-negativity of the random variable, because each value it takes is greater than equal to 0, and every probability is a number which is greater than equal to 0. So the first term is greater than equal to 0. And so I get that expectation of Z is greater than equal to whatever appears in the second summation. And because in the second summation, we are only considering values V which are bigger than T, I can write it as greater than equal to I can replace V by T, and that only decreases the summation. And here I'm just using that the probabilities are greater than equal to 0, which is always true for any random variable. And I can take T out common. It's the probability of all values greater than equal to T. So it's T times the probability that Z is greater than equal to T. So what we have proved so far is expectation of Z is greater than equal to T times the probability that Z is greater than equal to T. And just take T in the denominator or divide by T on both sides. So then we are done. It gives us that expectation of Z divided by T is greater than equal to the probability of Z greater than equal to T. Note that we are saying that T is positive. Otherwise, the bound doesn't make sense. And otherwise, we won't divide by T or sort of have the sign of the inequality preserved, etc. And of course, Z is non-negative, so T is always greater than equal to 0, but it should also be greater than 0 for this bound to make sense. In particular, actually, it should be greater than equal to whatever, or greater than whatever is the expectation for this bound to be interesting. Otherwise, we just get something which is even bigger than 1 and perhaps not so interesting. Is the proof okay?
Really quickly on the second to last line, how can we replace V with T?
We are just saying that, so look at each of these expressions. We have V times some probability, and I'm claiming that it's greater than equal to T times some probability because V is greater than equal to T. So I know that V is greater than equal to T. So then V times the probability that Z is equal to V is greater than equal to T times the probability that Z is greater than equal to V. Oh, sorry, Z is equal to V. Because I've just multiplied both sides of this inequality by a non-negative number. I know that V is greater than equal to T. The summation is only over V greater than equal to T.
Okay.
Right. So if since 2 is greater than equal to 3, 3 is greater than equal to 2, 2 is not greater than. So since 3 is greater than equal to 2, 3 times this probability is greater than equal to 2 times this probability.
Okay. Okay. Gotcha.
Right? So it's just multiplying both sides of the inequality v greater than equal to t by some non-negative number, which is the probability.
Okay. That makes sense.
Yeah. All right. So that's one inequality. And before we use it, let me just develop another inequality really quickly, compare the statements, and then we'll see sort of how the two are applied. And as I said before, a lot of inequalities are just developed by applying Markov's inequality, and that will also be the case for this one. So let's first understand the statement. So this is called Chebyshev's inequality. Here, this is for any real valued random variable. So in particular, I'm not assuming non-negativity of the random variable. It's just any random variable. It's still real valued because to compute sort of variance, we need kind of variance was defined in terms of by squaring some things and so on. And if it's not real valued, but it's a vector, it's not clear what that operation means. And there is some notion of variance for vector valued random variables, but the variance of a vector valued random variable itself is a matrix. So those things are a bit more complicated. Here we're just sticking with real valued random variables. And let's say we use mu to denote its expectation, although it doesn't. Yeah, so so mu is just some number. We are calling the expectation of z as mu just to write a sort of slightly cleaner expression. And then the bound says that the probability that z deviates by more than an amount t from its expectation. So z deviates from its expectation by more than an amount t is at most variance of z divided by t squared, or if you remember the definition of variance, it's just expectation of z minus mu whole square divided by t squared. We wrote two expressions for the variance. This is one of them. So it gives a bound, but it requires us to do something more. Instead of just being able to compute the expectation of this random variable z, it requires us to be able to calculate the variance of this random variables to apply this bound. And it's not always possible. It's a variance, as you might have seen already in the homework. It can be a bit more complicated quantity to understand than the expectation. But in case we can do that, we can potentially get a benefit of a stronger bound. Is the statement okay? Okay, let's assume that's a yes. So as in a lot of these proofs, it will just be applied, sort of just be obtained by applying Markov's inequality. And this is how. Okay. So let's say we define y as z minus mu whole square. So y is also a random variable. Right? Because if z is a function on the outcome space, then y is also a function on the outcome space. I've just kind of subtracted something from z and squared the whole thing. It's still a function. So y is a random variable. And in fact, y is a non-negative random variable. Because, well, it's the square of something and the square of a real number. And so and I can apply Markov's inequality, but let me just sort of check what I want to apply Markov's inequality with. So let's start with what we want to understand. We want to now to sort of try to get this to y, let's square both sides. So the absolute value of z minus mu and t are both non-negative numbers. So I can square both sides of the inequality. And I can say that the probability that z minus mu is greater than equal to t is equal to the probability that I square both sides. And this is equal to the probability that y is greater than equal to t square. Because y was just defined as z minus mu whole square. There it doesn't matter whether I have the absolute value or not. When I square something, the absolute value doesn't matter. And then by Markov's inequality, this is less than equal to expectation of y divided by t square. And expectation of y is just expectation of z minus mu whole square. In other words, the variance of z. So it's just a substitution. It's just a change of variable. And then we obtained the inequality we want by applying Markov's inequality to a slightly different random variable y. Okay. Any questions about the proof? Okay, so let's now see these in action. Let's at least get a sense of what are the kind of bounds these inequalities give and sort of how good or bad they are. Let's consider a sort of example of just sort of coin tosses, which we have been thinking about, or let's say xi's are independent random variables which are 0 or 1 with probability half each. In other words, each xi is a Bernoulli random variable with parameter half. And let's say z is the sum of n independent Bernoulli random variables, or in other words, it's a binomial random variable with parameters n and half. So, and for this particular z, we know how to compute both its expectation and its variance, and we did this when we defined this kind of random variables. The expectation is just by linearity of expectation. We can write it as summation of expectation of each of these xi's, and because each xi is just 0 or 1, its expectation is just the probability that it's 1, which is half, and so we get n times half. Right? And the variance of z we also computed, and in fact we used the sort of, in fact we proved this fact that it's the sum of the variances of each of these xi's, because these xi's are independent, and in fact we claimed that pairwise independence is enough. So partly we showed the proof. So the variance of z is the summation of the variances of the xi's in this case. In general, that's not true. So let me not write that as if it's an identity. It's just true in this particular case because of the independence. And the variance of each xi is, for a binomial random variable, is p times 1 minus p. So the variance is n over 4. And now let's see what bounds we get. So let's try to calculate the probability that z is greater than equal to 3n over 4, just as some threshold which is maybe somewhat far from its expectation, and let's see what each of these inequalities gives us. Markov's inequality will give us that the probability that z is less than equal to 3n over 4 is less than equal to expectation of z divided by whatever tail bound we are shooting for. Expectation of z is n over 2. The denominator we have this, which is 2/3. Which is still not bad. It's some interesting bound. It's certainly less than 1. So if we are interested in the event that z is less than 3n over 4, which is our good event, then this tells us that that happens with probability at least 1/3. this is better than the probabilistic method. We were just able to say that the probability is greater than 0. So it's some progress, but maybe not a kind of super high bound on the probability of the good event, or super low bound on the probability of this tail. Chebyshev's inequality will give us that the probability is z greater than or equal to 3n/4. First of all, we need to write it in the form of deviation from the mean. So this is actually the probability that z minus n/2 is greater than or equal to n/4. n/2 is just the expectation of z. That's why I kind of broke this into these two pieces. So it says that z deviates by at least n/4 from its expectation, and deviates on the positive side. It's kind of bigger than that. But you can upper bound it by the probability of deviation on either side. And by Chebyshev's inequality, we will get that this is less than or equal to the variance of z. The variance of z, we'll write in a minute, divided by the amount of deviation whole squared. The variance of z is also n/4. So one of these n/4s cancel, and we get 4/n. So this is a much better bound. In particular, this bound goes to 0 as n goes to infinity. So if you can calculate the variance, you get a much better bound. And in fact, you can even so there are two advantages to being able to compute the variance. One, you can get a very strong bound for the same amount of deviation, and you can also get some interesting bound for much smaller deviation. So let's calculate the following. So let's look at the probability that z is more than n/2, but only by a small amount, only by root n. And you can check that this bound sort of would have been just very, very close to 1 when we apply just Markov. It won't really have given us any interesting bound. But here we can. So this is less than or equal to the probability that so even a deviation of about root n from the mean, we can get a bound on, which is about 1/4, something non-trivial, even for this very small amount of deviation. And in general, this kind of bound is the reason for sort of so the square root of the variance is also known as, is also called the standard deviation. So you can check what we are really doing is that we're proving that even if you have a deviation from the mean, which is roughly comparable to the standard deviation, you can bound the probability of that kind of an event. So we think of a standard deviation as a good measure of the sort of the concentration of a random variable, or kind of don't expect the random variable to deviate much more than its standard deviation. It's because of these kind of bounds. Yeah. I mean, a lot of times when people apply this, they are kind of implicitly assuming some sort of Gaussian distribution, but not all random variables are Gaussian distributions. We haven't defined it yet, by the way, but if you know what that is. Okay. Any questions about these applications of the sort of bounds? Okay. So last few minutes, let me at least sketch how these kind of bounds can be applied, and these inequalities are relatively simple in terms of proofs, but they already have some very interesting applications. And in particular, one sort of nice illustration which kind of I like because of the exercise in computing variance is and then sort of the maybe somewhat striking conclusion is the existence of what are called threshold phenomena. So it's and let me first define it in graphs, although these kind of phenomena can be defined in more general settings. So let's say we have a distribution on graphs, which is parameterized by somehow how many edges a typical graph in this kind of a distribution has. Formally speaking, let's define this distribution G and P. So G and P is a distribution, not a random variable. A graph sampled from this distribution is a random variable. And by the way, I'm talking of a graph as a random variable. This is not real value, but we will define other real valued random variables where we'll apply Markovs or Chebyshevs. So going back, we're looking at a distribution on graphs with n vertices. And we define this distribution by saying that for every possible pair, we put an edge with probability P. So we look at each pair and we independently decide whether to put an edge or not. Okay, so another way, each edge is a Bernoulli random variable with parameter P, and all pairs in the graph correspond to independent Bernoulli random variables. So it's just a collection of independent Bernoulli random variables, but we choose to view them in the structural way of a graph. Okay. And what we are interested in is this graph exhibiting some particular kind of behavior, some property. And I'll say something about this sort of phenomenon is true in general for any kinds of properties which are monotone. So whenever we kind of add edges, we expect the property to only become kind of more likely, or sort of if some graph has the property and we add a bunch of edges to it, we cannot destroy this property. So this property can be anything. It can be that the graph is connected. It can be the graph has a certain kind of path. It can, and then we'll see an example of this property in a slide. But the goal is to sort of understand what is the probability that a graph sampled from this random distribution, from this distribution G and P, has some property we are interested in. And also, we are interested in understanding this probability as a function of P. How does this probability change as P changes, as P increases? And the reason we call this sort of behavior as a threshold phenomenon is that in a lot of cases, we observe that, well, up to certain values of P, the probability is essentially zero. It's very close to zero. And then within the relatively short interval, it sort of shoots up. And yeah, I mean, the interval is much shorter often even than what I've drawn. And then it's essentially close to 1. So it's probabilities are between 0 and 1. And let's say it just shoots up from 0 to 1 very quickly. And often it's much more dramatic. It sort of really shoots up depending on how you draw this graph. And in fact, there is a whole industry of bounds in terms of understanding how fast does it shoot up. So what is the sort of sharpness of this threshold, as it's called, and so on. And also exactly what, so we know that sort of after this threshold, the probability is essentially 1. Before this threshold, the probability is kind of essentially 0. What happens at this threshold? And again, these are very interesting things which are studied a lot in random graph theory, and more generally, these sort of threshold behaviors also happen outside of graph theory. In fact, there are many interesting examples which are not graphs. And a good place to look it up is also the book by Allen and Spencer I mentioned last time. It has some very nice analysis related to threshold phenomena. But going back to graph properties, let's say we are interested in the following. So we have a big graph G, and we are going to say it has a property or not in the sense that whether it contains a copy of some fixed small graph H or not. In this case, H is a small graph with 4 vertices and all 6 edges present. It's also called the 4-click or K4. So that's just a special name for this particular graph. And you can ask this question for any H. And what does it mean to say that G contains a copy of this graph? In this case, it means that G contains some 4 vertices with all 6 edges. So, for example, in the graph that I've drawn, this is a 4-click. So these are 4 vertices with all 6 edges present. Here's another one. Well, actually, maybe we can modify the graph to give you another one. But here's another one. And so on. So are there 4 vertices with all 6 edges between them present? Maybe there are other ones, but so that's just our definition of what it means to say that G contains H. And an interesting phenomenon is that there is a certain kind of threshold for this probability, in this case, n to the minus 2/3. So when P is, and by this notation, I mean that the limit of P divided by n to the minus 2/3 goes to 0 as n goes to infinity. That's just P is kind of much less than n over n to the minus 2/3. And here, I just mean that the limit of P divided by n to the minus 2/3 goes to infinity. So, and this is what would be called a coarse threshold. There are much kind of finer estimates on bounds for P. But let's prove this, and then I'll at least state the bound before we break for today. So, what you can show is that the probability that G contains a copy of K4 goes to 0 is essentially 0 for larger and larger graphs when P is significantly below n to the minus 2/3. And it's essentially 1 when P is significantly above n to the minus 2/3. And let's at least see a quick sort of reason for why to expect this. So as usual, we can write Z as a sum of indicator random variables where the C is just a subset of V of size 4. So it's just some set of 4 vertices in the graph, and XC is equal to 1 if all 6 edges are present. So notice that I choose not to care about the ordering of these 4 vertices. As long as I have the set of vertices 1, 2, 3, and 17, it's the same as 2, 3, 17, and 1. I don't really care about what order I look at this set of size 4. An expectation of Z by linearity can be written as, so I'm just counting the number of copies, which I'm just defining to be equal to summation of X sub C. The number of subsets of size 4 in the graph with n vertices is n choose 4. And for each of them, the probability that all 6 edges are present is P to the 6. because there are 6 edges which have to be present. Each of them is independently included in my graph in GNP with probability P. So it's n choose. And you can see that this goes to infinity when P is much larger than this threshold of n to the minus 2/3, and it goes to 0 when P is significantly smaller than n to the minus 2/3. So at least the expectation kind of follows some sort of behavior of 0 or infinity, and this can be translated into the probability being very close to 0 or 1. We'll talk about it in the next lecture, although yeah, you can take a peek at the next slides if you want to sort of try working on the proof yourself. I'll stop here for today. Okay. Any questions?